Let's quickly go through the recap of Laplace transforms. Okay. So we know that uh, whenever we have a function or signal, right, it has some characteristics such as it is going to vary, it is measurable, and it's going to provide you some kind of information. Right. So that kind of function is what we call as a signal. Basically, it's a function. Okay. Now, for example, we can see on the left hand side, there is a temperature data of versus time, right? So we can see that it is varying and we can measure and it is providing an information, right? So transforms are basically used to convert the functions from one domain to other domain. For example, left hand side is time, right hand side is frequency. So most commonly used domains in our field are these two. There are even multiple other domains, right? So whenever you take a transform, you try to change the domain of the signal. All right. Function changes its domain whenever you take a transform. So you see that the right, if you want to go into a frequency domain, the tool used is called as a Fourier transform. Okay, right. Now, if you recall, there are some issues with the Fourier representation, right? The basic differences in terms of the Fourier representation include every signal will not have a Fourier representation. That's the problem, right? So whenever a signal has no Fourier representation, but still you want to, you don't want the time domain view, you want to go to a different domain, right? Means you have to go for a different transform. So the solution comes in terms of the Laplace transform, right? Where for those signals which do not possess a Fourier representation, in the sense it does not have a Fourier transform or Fourier series representation, you can go for a Laplace. Okay, it's a very similar tool like Fourier, but provides much more detailed view. Plus, it's also going to give you uh, something like whenever you don't have a frequency representation, right? It takes you to a different domain where you can visualize and process the signal. Okay, so that's the characteristic. Now, so the general equation is f of t in time domain. We'll write an arrow mark saying that there is a L, which is a Laplace transform. So since the domain is not frequency, we will not write it as a term f or omega. We have to call it as a S domain. Okay, so the right hand side is S domain. So time domain is f of t, capital F for the changed domain, then the domain variable is S. So how to write the equation? The equation for Laplace transform is capital F of S is Laplace of f of t, which is 0 to infinity. You integrate f of t into e to the minus st dt. So what's the difference between this equation and the Fourier transform equation? It's the S instead of S. In Fourier, you have j omega. Okay, and so if you remember, it's integral minus infinity to infinity f of t e to the minus j omega t dt is Fourier. So what? Right. So correct. So if you want to relate the difference, relate the two domains like S and omega domain, you can replace S by simply j omega to get the Fourier transform. Okay. But the S actually corresponds to a sigma plus j omega. Normally, it's S is not simply j omega. S is equal to sigma plus j omega. The sigma comes into picture because you want to scale your Fourier transform to get into the S, right? Okay, so that's why, right? So if you simply write minus j omega, right? Sometimes Fourier has no answer. Okay, there may be a case where the integration is not possible. Just to avoid that, you put a sigma plus j omega over here, which makes sure that the function is integrable, right? So if you remember, when we studied Fourier, there are three conditions to be met by a signal in order to possess a Fourier representation. correct? So Dirichlet conditions, right? Signal should be absolutely integrable. Finite number of discontinuities should be there, right? And in one period there should be finite number of maximum or minima values, etc. We have some conditions, right? But in case of if Laplace, you don't have any condition because the S takes care of everything. Okay, fine. So that's anyway, I'm trying to skip the part because that if we go very much in detail about that, it's going to take a lot of time. Okay, fine. Now, whenever we take a transform, the definition of transform is nothing but changing the domain from time to frequency or time to S. If you go, there should be a facility to come back. Okay, I have given S domain function how to come back to time, right? So that also should be right, we should be able to do that, and that is called as a inverse Laplace transform. Okay, so f of s is given, you apply the inverse Laplace L inverse to come to the f of t, the time domain. Okay, right. So this is what the introduction we need. Directly we'll go to some problems. Okay, fine. So let's see, the f of t is equal to t from 0 to 4, 5 t greater than 4. Okay, if this is given, right, so we directly apply the uh, definition. Definition says 0 to integral 0 to infinity f of t e to the minus s t dt. But it's not the same function from 0 to infinity. There are two parts. First part is 0 to 4, so I have to split the integral 0 to 4 t into e to the power minus s t dt. Then the second part is plus 4 to infinity 5 into e to the minus s t dt. Okay, fine. Now the first part, if you see, we are right where it's a product rule, t into e to the minus est, correct? So how to integrate that? We have many options, right? So the first one is you can simply apply the product rule. First function as it is, I keep t as it is. E to the minus est, you integrate. So this becomes e to the minus est by minus s. Bernoulli's rule. All right. So second term, it's minus. Differentiate the first term. You see, you have t over there. T differentiates to 1. Okay. So this t differentiation is 1. Are you okay? And the e to the minus st by minus s, whatever we have here, I should integrate this further because it's the Bernoulli's rule, right? So first function keep as it is, second function keep integrating, right? And when you go to the next term, differentiate the first term. So t becomes 1, and in the next case, you can see that that 1 becomes a 0, right? I have put an arrow mark showing that this becomes equal to 0. All right. Okay, so plus there is another term, right? So you can see that this is still there, right? That we are integrating. 5 is a constant. 5 into, it's just e to the minus st. So integrate e to the minus st by minus s. Okay, just go through this step, and if you're fine, I would like to proceed. This step is over. All right. So now let's substitute. So the upper limit is 4, lower limit is 0. So when you put t is 4, this becomes 4 into e to the power minus 4s minus, when t is 0, it is 0. That's the first bracket over here. Okay. And the next one, it is, I take 1 by s square outside, put 4 once again, it is e to the power minus 4s minus, whenever e to the 0, it is 1. So that is the second term. All right. Then the third term is anyway 0. The fourth term is 5 into, put e to the power minus infinity, that's why it is 0, minus e to the power minus 4s. Okay, so that's what we are going to get now. So in the next step, we simplify this further, eliminate all the zeros and write the term, and you are going to get the answer like this. That is a simplified answer.
Yes.
Okay, please go through this. Let me know if you have any doubt. go to the next question, right? This is f of t is sine 2t whenever the t is between 0 to pi. Okay, for other values it is 0. So it like there is a time limited signal, so function is only between 0 to pi, right? So f of s is equal to 0 to infinity f of t e to the minus st dt. Okay, so this means I can integrate now only between 0 to pi sine of 2t e to the minus st dt. Okay, now which function, how do you simplify this, right? It's just mathematics because as of now no concept in Laplace has been discussed with respect to the control system or any other subject. So it's just mathematics. Can you suggest a method to simplify this? E to the minus st sine 2t dt. Okay. There are multiple methods, multiple solutions. Yeah, you please go ahead. Yes, maybe. Hmm. We can see a product here. Maybe one option has to be the application of a product rule, right? Okay. Hmm. Okay. Okay. So what's the first step? What is the condition for applying the Bernoulli's rule? Because previously we applied the same Bernoulli's rule, right? We had a product and we applied. But is it possible to apply now? Is the second is my question. Maybe it's possible, but is it easier like the previous one, or do you have any problem applying? We can apply, but I think this is going to be more tedious in this case. Okay. So what is the? It's because of presence of which term? You are right. It's going to be difficult in this case. That's right. But why? What's the difference between the previous one and this one? Right? So because of that, we cannot go ahead with the that part, right? So initially it is sine, next cos, then sine, then cos, etc. Right? So you keep on. So it's going to be infinitely long, right? So this. So you have a solution. You have a standard form. If you look carefully, this is e to the power at sine bt. Okay, so whenever you have that, you can see this. It's a direct form. You don't have to do any integration. Simply look at the form e to the at sine bt, where a is the minus s and b is equal to 2. Right? Simply apply that. So when you apply that, e to the at, so the answer, you can see that e to the at by a square plus b square. So e to the minus st by minus s whole square plus b square, which is 4, into minus s into sine 2t, because a sine bt minus b cos bt. So 2 cos 2t will come into picture. You need to substitute the limits 0 to pi for t, correct? So we'll apply that now. So when you apply the t value to be pi, right? So sine 2 pi becomes 0, cos 2 pi is going to be 1. Okay. Similarly, when you put 0, sine 0 is 0. Once again, cos 0 is also going to be 1. That simplifies to minus pi s square plus 4 e to the power minus s into pi minus 2. Just go through this step once, the substitution part, these two. Let me know if you have doubt. Otherwise, we'll move on. Yeah, sure. Okay. Right. So then we'll take the minus sign inside and take a 2 outside so that you get this as the final answer. Okay. So the next question, this is pretty straightforward, right? We have e to the t from 0 to 1. So integration happens only between 0 to 1, right? Function is e to the t into e to the minus st dt. So we can take the exponential terms common, right? So t will be taken out, and when you club it is 1 minus s into t. So integration is e to the 1 minus st by 1 minus s. When you put 1 over there, it becomes e to the 1 minus s. When you put 0 over there, it is simply e to the 0, which is 1. So this is the answer. Okay, yeah, we'll move on. Just check this. It is, I'm supposed to perform the function as it's defined only between 1 and 2. Okay, and the function is t. So instead of substitution from 0 to infinity, you need to substitute only between 1 and 2, and the function is t into e to the minus s. Okay, so this is now you can see that you can apply polynomials, right? So t as it is, right? The second function you can integrate. Next, the definition differentiation of one t becomes one, and hence next stage it becomes zero. So after that you don't have to do simplification further. Okay, so do that and put the limits as 1 to 2 is right. I can see that the 1 by s can be taken out from the first term. Put 2 over there, it is e to the minus 2s. Put 1, it is e to the minus s. Similarly, for the second term, we'll take minus 1 by s square outside. Put 2 over there, e to the minus 2s minus e to the minus s. Now for the simplification, you can keep it that answer as it is. Okay, right. So yeah, please take this question as a homework question, right? All right. So this is just an introduction how to solve basic questions. So Laplace transform based on the definition. Okay. Now we move on to the standard functions, right? So first function is a constant, right? F of t is equal to a. If there is a constant, what happens to the Laplace, right? You can see that I am doing the integration 0 to infinity a into e to the minus st dt. Again, we are applying the standard definition itself here. Okay. So a is a constant. E to the minus st integration is e to the minus st by s. Put the limits 0 to infinity, and this is the answer. Correct. Right. Right. So because of that, so we can consider this as the standard first standard entry. You can make a table for your reference. If instead of a, if you write 1, it is, so this is the example direct application of this. So if you give 1, Laplace is 1 by s. Yes, correct. So that's the first one. right? Just make a note of this. That's all. You can apply this later. Okay. Then the next function is increasing exponential e to the power at, right? So if e to the at, then we'll apply the same definition: 0 to infinity f of t e to the minus st dt. Okay, so that means integral 0 to infinity e to the at e to the minus st dt. So clubbing the terms, so we get this. So once that is done, now you can integrate simply e to the minus s minus at by minus of s minus a for the limits 0 to infinity. When it is infinity, the value becomes 0. When it is 0, it is 1. Right? So since the minus of minus gets cancelled, so your answer is this. So this is the standard entry that you are going to put into the table. If the function is e to the at, Laplace will become correct. Alright, then similarly, again, you can directly note this. If the a becomes minus a, e to the minus at, only the sign of a will change in the previous answer. Okay, so it becomes 1 over s plus a. Sign change. Now, the next, huh, right, right. So this is the example for that. If the function is cos hyperbolic of the at, we know that cos hyperbolic function can be represented as a e to the at plus e to the minus at by 2. Right? So what we do, instead of f of t, we'll write the e to the at and e plus e to the minus at. We'll take it out because it is a constant. So now, as soon as we do that, we can split the integrals, correct? So the integrals get split, and you can see that the first term is 1 over s minus a. Already you have solved. You don't have to do it again, right? So e to the minus at is 1 over s plus e. So, right, we know them. We directly substitute and then we simplify. Take a common denominator. S minus a into s plus a becomes s square minus a square in the denominator, and this s plus a comes over here, this s minus a comes over the other side. Correct? So because of that, you can see the simplification like this, right? In which we can see that the a and minus a will get cancelled, and we have s by s square minus a square as the answer. So this is the next entry in the table. Cos hyperbolic of at has a Laplace transform s by s square minus a square. Okay. Next one is sine hyperbolic. So sine hyperbolic is defined as e to the at minus e to the minus at by 2. Everything remains same. You can see the steps, and only change is the minus sign in the middle. So because of the minus sign, the s will get cancelled now instead of a. So the final answer becomes a by s square minus. Okay, so this is the right there. Now we go for the next one, that is cos 80. Right? Cos 80 e to the minus st dt. So this is a standard function once again. So you don't have to integrate. So integration of e to the at cos bt dt is nothing but e to the at by a square plus b square. Now the function changes to a cos bt plus b sin bt. Previously it was different. So right, whatever I have highlighted using the red border is the formula which we are going to use now. Okay. Correct, correct. Yes, correct, correct. So we have two functions. One is e to the at sine bt. Second one is e to the at cos bt. So if we remember that formula, we can apply any point. So the same thing we are applying now. So we just compare what is a and what is b, right, in the given question. So we substitute accordingly, and we put the limit from 0 to infinity. So when you do that, right, this is the answer what we are going to get. So if it is a cos at, s by s square plus a square is the answer. Okay, right. Then we move on to the next one. This is sin 80. F of t is sin 80. So once again, it's the same previous property we are using. Sin 80 into e to the minus st. I'm going to integrate. So you see the change in the formula now, right? The sign will change in the middle. There is a minus coming up. So instead of cos, we get a sign at the as a first term. Right. So e to the at by a square plus b square, a sin bt minus b cos bt. This is what we need to substitute. So when you do so, right, again put the limits 0 to infinity, compare a and b according to the problem, and put the limits. So at the end, we can arrive at this answer. Okay, so this will be the next entry in your table. Sin at has a Laplace transform s, sorry, it's a by s square plus a square. Ha. Yes, 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 yes. True, 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 true. Correct. So there is another option to solve this. You can try this later. Instead of using the integral, the properties of integration, you can substitute cos at as this, or even the sin at as this. That's also good. F of t, right? Yes. Then you can actually multiply by e to the st to this, and you can solve. Okay. It's also going to give you the same answer. You verify. Let me know if you have any doubt in that. Okay. Let's move on. Yeah, denominator will get a j. Difference is that you have j present over here, right? Yes. That's the difference between hyperbolic function and a normal function. Okay, right. Let's move on to the next one. It is t to the power n. Right. So function f of t is t to the n. So we are supposed to perform the integration 0 to infinity t to the n e to the minus st dt. Okay, so t to the n, I can see that since n is unknown, right, you cannot go ahead with the differentiation and integration altogether, right? So that is not possible. So we go for a method called substitution. Put x is equal to st. So e to the power, it becomes e to the minus x. That's why. Okay. So dx becomes s into dt. So I have a dt to be substituted in the equation. So dx by s. Every term in the equation should be represented in terms of the substitution what you're going to make. Okay, so and the limits also should be changed. So t equal to 0, right? So t0 means x is also 0 according to this equation. Put t0 x0, t infinity x is also infinity. That's why we have these two. This is the change of limits. Okay, according to the new substitution what which we made now. So directly we convert this into this. Okay, just see the changes on in terms of the substitution. T becomes x by s. That's right. Huh. Yes, e to the power minus x into dx by s as per the substitutions made. Again, we made the changes. It's not t now. It is in terms of x. So once that is done, now you see this is. You can see that there is a s to the power n and a separate s. So you have s to the power n plus 1 in the denominator. Then you do the integration 0 to infinity x to the n e to the minus x dx. If you remember, this is a special function called a gamma function. So this is gamma of n plus 1. Okay. So that means I can call this function as a gamma of n plus 1. So directly I'll replace gamma of n plus 1 by s to the power n plus 1. So t to the n, this is the ultimate result. T to the n has a Laplace transform gamma of n plus 1 by s to the power n plus 1. Okay, so this is again, this is applicable for something like any n, right? Any rational value of n, etc. But now let's go for a specific case and check what happens when n is integer. Okay, so previous case n works for anything, right? Any real value, right? But now we make sure that n is only integer. When n is integer, we have a specific property of gamma function. Gamma of n plus 1 is simply n factorial. Okay, so that means f of s becomes now it is n factorial by s to the n plus 1 only when n is integer. Okay, so you see that this is the updated rule. Okay, if n is integer, then t to the n will have a Laplace transform n factorial by s power. You don't have to find a gamma value for that. Okay, yes, we have a proof in that in maths. Function becomes n factorial. Okay, let's move on. Let's go for some of the simple problems based on what we already have studied. Okay, just now we derived everything. Just verify. I'll whole thing, right? Just verify one by one and let me know if you have doubt. Otherwise, we'll keep going. Okay, just go through all of them. Okay, check this one. S by s squared plus a squared. Yeah, that's right. Next one is this sin 80 format. Yeah. Okay, is it fine? Because the 6 comes to the numerator as a root 6. Hmm? Yes, yes, yes. Then check these two. Right. Correct. Check the next one. Okay. The next one. This is cos hyperbolic square of 3D. Yes. Next one. It, it gets multiplied. E to the minus 2t into e to the 4t is e to the 2t. Yes, correct, correct. Actually, you have many other methods, right? But this is the easiest one. Okay. Okay. All right. Is it okay? Right. Hmm. Correct. Okay. We get the standard format and we can substitute. Question is f of t is equal to sine square of 2t plus 1. Have a square term, I don't have a direct conversion, right? So I prefer to write it as a 1 minus cos 2. So 2t plus 1, is it? Right. And that it becomes a straightforward function. Okay. Go to the next one. Try to solve this. Straightforward. Okay, just go through this. Yes, 5 to the power t. E to the t, we don't have a to the t. Okay, so you convert that as e to the power at. Okay, so log and e to the power are inverses of each other. They will cancel out. Alright, so because of that, we'll write in this form. Okay, this is the next question. 3 root t plus 4 divided by root t. There is a function, it's a property of a gamma function. Gamma of 3 by 2 is half into root pi or root pi whole by 2. Okay, yeah, this is the one. So gamma of 3 by 2 is this whole thing. root pi. Okay. Then this is the next one. Okay. This is root t minus 1 by root t whole power 3. Right. So the root t will write as t to the half. 1 by root t will write as t to the minus half. There is a raised to the power 3. So we expand. So each term has a t to the n format. N varies. So for according to the n, we'll write this. Yes. Correct. Yeah, so every value is a standard gamma function. You will substitute, okay, and then you get the final answer. Yes, yes. Go to the next one. Okay, the next is t to the minus 5 by 2 plus t to the 5 by 2. Again, this is a standard one. T to the n, we'll put it as a gamma function and we'll simplify. Substitute every gamma value over there and you get the final answer. It's a straightforward one, okay? So we know we have to remember the gamma values, that's all. Then now let's move on to the some of the properties of Laplace transform. The first property, anyway, there is a linearity. We'll skip usually because linearity is very simple. A into a function plus b into another function is same thing happening on the frequency side. Okay, so that's why we skip that. So we'll go to the only the important properties. So one is a S domain shift. Okay, so always the definition goes like this: for a given function, what is its equivalent Laplace? We know. That's why f of t has a Laplace f of s. This is known to you. Then for that function, if you multiply by e to the at, right, simply replace every s by s minus a on the other side. Okay, we'll try to prove this now. So f of s is, right, from the basic definition, f of t e to the minus est dt with the integral 0 to infinity. But if you have e to the at f of t, what happens? The e to the at f of t will come in place of f of t. That's all. So I can see that e to the at's can be clubbed with e to the minus est to get this function, right? So if at all this whole term was simply s, I used to write a s here, correct? But now it is not. Yes, it is s minus a. So it is f of s minus a. Very straightforward. Okay, just see this and let me know if you have doubt. Right. So the entry that we can make in the table is like this. E to the at f of t will have f of s minus e on the right side. Similarly, if you write e to the minus at f of t, Laplace becomes capital F of s plus e. Yes, this is called as S domain shift. It is s minus a, right shift. S plus a is the left shift. Shifting happens in the, so it's the same similar property we see in other transforms. Okay, if you multiply by an exponential in the time domain, right, that is corresponding to a shift in the other domain, right? Same thing, if you multiply e to the j omega t f of t in Laplace, sorry, in Fourier, it becomes the f of x minus omega, right? So that's same thing. Okay, right, let's move further. The next one is derivative of S domain or the differentiation in S domain. It's called as differentiation in S domain as well. So the definition goes like this. For a given f of t, let us assume that we know what is f of s. After this condition, right, if you have t to the n into f of t, the original f of t gets multiplied by a t to the power n, right? This indicates the f of s which we had earlier, right? This gets differentiated n times, dn by ds to the n comes into picture, into a multiplier that is minus 1 to the power n. To prove this, so we start with the definition f of s is equal to this. Then so if we differentiate with respect to s on both sides, left hand side is d by ds of f of s, and the right hand side becomes, it's a differentiation of that integration, but we cannot cancel them because differentiation happens with respect to s and integration is happening with respect to t. So ds and dt will not cancel. Okay, this ds and dt. So integration and differentiation will not cancel. All right. So it means you can actually bring the d by ds inside the integration and you can apply to that term which has a s. So which is the term that has s? It is e to the power minus st. Have e to the minus st, I differentiate, it becomes minus t into e to the power minus st, because differentiation happens with respect to which one? With respect to s. So t is a constant now. Okay, right. So this means minus t into f of t has a Fourier transform, sorry, has a Laplace transform d by ds of f of s. That's what is the meaning, right? So which means you can just see here. So this is how we write, minus t into f of t means d by ds, right? Take the minus to the other side, t into f of t becomes it's minus 1 d by ds of f of s. Now what we do, we'll try to apply this like this. Now you see, first we assume that this is a standard procedure in mathematics. When you get a result means you can actually extend that result, right? So this is, so anyway, let's assume that this is true for n is equal to 1, right? Because t to the n is equal to 1. So t into f of t. Now let us assume that this is true for any k value, right? So t to the k is f of t is minus 1 to the power k into dk by ds into f of s, right? This is what is the assumption. But now if any k, if it is true for any k and you make sure that it is also true for any k plus 1, which means it is true for everything, correct? Because now already we proved for 1, right? If it is k plus 1, 1 plus 1 becomes 2. So 2 plus 1 becomes 3, 3 plus 1, it's true for every number, right? So we can prove like that. So what you do, you differentiate this assumption once again. So t to the k as, right? So minus 1 to the k, d to the k plus 1 by ds to the k plus 1 into f of s equals to, right? So what happens to the left hand side? It is t to the k into f of t was there, right? D by ds of e to the minus st dt. So this is the term I'm going to get. Anyway, I'll try to bring the minus to the other side, right? Minus 1 comes to this side as minus 1 to the power k plus 1, right? Then I already have the d to the k plus 1 by d s to the power k plus 1 already is there. And the integration inside I just have t to the power k plus 1 into f, which means it is a Laplace of t to the k plus 1 into f of t, right? So for any k it is true, and for any k plus 1 also it is true, right? This means it is true for any value n. That's why this is the, yeah, yes, correct. So yes, so that's the standard way, right? So you first you prove that it is true for 1, then you assume that it is true for any k, then you prove that any k plus 1 also it is true. That is done, then this is, it's true for anything, right? Like that we can prove it. Right, so two properties we covered today. We'll stop here and let's continue to the next remaining properties and the problems based on that in the next class.